Good morning. Your assignment, if you choose to accept it, and you will, is to do worksheet 3 today as one of the things you'll do in class, qualitative energy storage and conservation with bar graphs. I will explain. I will do 1A as an example and to explain everything uh, in the diagrams that you need to consider and what you need to fill in. You see a diagram here that has a spring and a cart. Assume the spring is compressed in situation A, and then the spring will release its energy and push the cart, and then there's situation B to consider. You see the cart is moving at the top of that loop there. You will analyze energy storage using these energy bar graphs. So not pie charts now, but bar graphs, still simple. And this would be position A's bar graph, and then this is for the situation position B, the bar graph here. You'll recognize kinetic energy, gravitational potential energy, and EL for elastic potential energy. And that is the starting energy situation. And the final energy situation, you have the same three energy storage modes, but there's also this ETH, that is thermal energy, but I like to think more general, as we have learned in class, as dissipated energy. So you can make that dissipated energy to be consistent with what we've done. In the middle is the system and flow chart. We put down what's in the system. In this case, we would identify the spring as part of the system, the cart, and there's only one cart in two different situations. There is going to be some elevation, so we'll want to have the whole mass of the Earth as part of the system so that we can have conservation of energy. And we're considering dissipated energy, so we're going to want to have the air here as well. So we put down our list of items in the system right there. This is really where you start. Flow here is for the situation where perhaps there's energy flowing into the system or energy flowing out of the system. That will happen once in this worksheet. Otherwise, that doesn't happen, but it is possible, and we're preparing for later possibilities. It will occur once, I think, in problem number 6, 7, or 8, something like that. So let's make the bar chart for situation A. That is a compressed spring. The cart is not elevated. We will assume that this is the zero height level. So there's no, it's not moving, so there's no kinetic. It's not elevated, there's no gravitational, but the spring is compressed, so there is elastic potential energy. So in fact, I'll say there's a full set of 1, 2, 3, 4, 5 bars worth of elastic potential energy. After the event, the object is moving. You can tell by those lines right there. So there's kinetic energy. It's elevated, so there's gravitational potential energy. The spring has released its energy, so there is no elastic, and of course there will be dissipated energy. So just like the pie charts here, this is guesswork, but since there were 5 bars worth of energy to start, let's go with, say, 2 bars of kinetic, 2 bars of gravitational, and 1 bar of dissipated energy. So energy is conserved, and we show it here with our bar graphic. Lastly, the qualitative energy conservation equation. Well, that is essentially the idea that the initial energy equals the final energy, meaning energy is conserved, which means I can say over here, this energy right here, the elastic potential energy, must be equal to the energies that I have over here, which would be kinetic energy plus gravitational potential energy plus the dissipated energy. And these are just general qualitative energy equations we're going to write on this worksheet. In the future, we'll be writing more detailed and quantitative equations. So your job is to do this for all of the questions on the worksheet, and I'll give one more example, and you'll do the rest. All right, here's 2A as an example. A car rolls up a hill until it stops. Do this problem for a system that involves the car, the road, and earth. Assume the engine is turned off, the car is in neutral, and there is no friction. Down here, VA means the velocity in situation A is equal to 0, and I'm sorry, YA, that's the elevation is 0, so that's the 0 height level, and VA, the velocity, is greater than 0, so it's actually moving here. Here, the Y position is greater than 0, so it's elevated, and the velocity is 0 up at this point right here, so it's at its peak. So analyzing this, in the beginning it has kinetic energy. It does not have any gravitational, and there's no springs or flexible material. So it's 100% kinetic energy. And situation B, it is not moving, but it is elevated, and there's still no elastic material, but there is going to be dissipated energy. So let's say 4 bars of gravitational, 1 bar of dissipated energy. And the equation then would be that the kinetic energy in situation A must equal the gravitational potential energy plus the dissipated energy in situation B. So there's an example, and I hope this is enough for you to do the rest successfully. Good luck.